Thanks for the gentle introduction. And I was originally thinking about visiting Australia for this talk, but unfortunately, because of all the current prevailing situation due to COVID, um, we have to go remotely. But I had the pleasure of visiting Australia in 2015. My wife's folks live there, and I visit Brisbane most of the time. So it was a pleasure to introduce Apache Pulsar to the Australian audience. So anyway, so let me start. So my name is Karthik. I'm currently the Senior Director of Engineering at Splunk. So before Splunk, I had a streaming company called Streamlio. 6 months ago, it was acquired by Splunk. And before that, I was at Twitter and working on a lot of the streaming at a high scale. And before that, I had a company called Locomatics that got acquired by Twitter. So that is my short bio. So let me start the talk. And so I think there is a question and answer session after the talk is finished for 25 minutes. So I will try to answer as many questions as I can in the Slack itself. So let me start the talk. So we are in an increasingly connected world where a lot of sensors are being attached to several devices of several kind. So which means the data collection mechanism is improving. So which means the data is coming at a high velocity across at several devices and sensor at a high scale. So that leads to the ubiquity of real-time data streams and events. So now the question is, when you have such a deluge of data coming from these several sensors embedded in cars, phones, as well as healthcare devices, factory floors and manufacturing floors, etc., how are we going to deal with this data deluge, and how are we going to process the data in real time? And that's all constitute what we call as a event / stream data processing. So what we do in events are stream data processing. Events are analyzed and processed as they arrive. Decisions are very timely and also contextual and based on the availability of the fresh data. So the data, the analytics, the value of the data is very high when it's fresh. Then it slowly decays into an asymptotic as it goes into a number of days. So the value of data, if it is processed immediately in a few milliseconds versus seconds versus minutes versus days, there's a difference in the value of the data. So because of the fact that the data is fresh, the decision latency is eliminated. You can make decisions as quickly as possible. And sometimes stream data processing is called even data in motion processing. So at a high level, you have these three different type of rocks within the stream processing. One is you have to ingest the data and buffer the data. Then you have to analyze the data, and then you have to act on the decision that you've made. So if you look at the different patterns where the streaming is applicable, one huge block of area where streaming is applicable is something called monitoring. Monitoring in the sense of you want to monitor your machines, you want to monitor healthcare devices, you want to monitor some temperature of sensor embedded in a tree, in a forest, or so those kind of aspects are called, you're getting the time series data and you're monitoring the entity that you are interested in monitoring for. So those broad pattern of monitoring falls into a stream data processing because data is coming continuously arriving from those devices or sensors, and you're looking at the data in a continuous fashion. Second one is the microservices, where the pattern is where you break down the monolithic application into smaller services, and in these smaller services, as you can think about as a streaming pattern where a request comes in, it has to hop through these multiple services and get back as a response. So this can be viewed as a streaming as well. The second one is where you have what you call streaming workflows, where you process the data, then pass on to the next person in the workflow, then pass on from after that is finished, pass on to the next stage in the workflow, and so on. So that is, again, it's a streaming flow. Then model inference. So for example, in machine learning model serving, you have the model that is built up. This model can be served using data that is coming online, which lookups into a model and gives a score. And that can be thought of as a streaming as well. And in fact, you can even think about the model as a streaming, which is a control stream where the data from model is kind of updated on a regular fashion periodically. Then the data is also scored along with the model updates. So then the final pattern is called analytics, which is the streaming analytics, where people join multiple streams and aggregate on top of the streams to provide some view about how my ads are looking like today or during the Super Bowl time or during Oscars time. So those kind of insights are more streaming analytics. So in order to do all these various different stream processing paradigms, so at the underlying infrastructure or the data infrastructure, there are three things that you need to remember to bring together. One is the messaging, where any streaming system need to have a notion of ingesting data. Then the second aspect is the storage the data, where we need to store the data in storage so that you can process the data in real time or even access the data whenever we need to, or if there is a lag in the processing, then you can go back in the data, replay the data. Those aspects are in the storage. Then we have to do something with the data. That is where the compute comes in. So you have to look at the data, mine the data from a data enhancement point of view, data processing point of view, those kind of aspects. So that is where, so which means in order to do end-to-end stream processing, you need to have messaging, storage, and compute all have to come together. But if you look at the entire open source ecosystem, a lot of solutions are kind of piecewise. Messaging one system, compute is another system, storage is another system. So you have to bring in several different systems together to stitch them and do an end-to-end processing. So the problem with that such issue with such systems are each one has its own natural evolution, and it's not tightly integrated with respect to end-to-end stream processing. And maintenance and operation aspect of such multiple systems in order to stitch together becomes so expensive because you need to have a different type of data engineering talent, different type of operational talent. So which means the business value that you realize out of streaming goes down because the cost of delivering the streaming infrastructure is pretty high. So that is why Pulsar is the first system that tries to bring all these things in three things together. So what is Pulsar? It's nothing but a flexible messaging plus queuing system with the compute embedded into it, and it's backed by a durable log storage. So now let us look at this is the one sentence version of Pulsar. Now let us look at some of the key concepts in Pulsar. So Pulsar has this notion of what you call tenants, because it's naturally a multi-tenant system. It has a notion of a tenants, and it has notion of namespaces, and it has notion of topics. So you can think about a tenant is some kind of a department within an enterprise. And within that department, you have multiple applications that each department is in charge of. Then within each application, there are a bunch of streams on the data and the compute are collected together, right? So that is why Pulsar allows this three-level hierarchy that naturally supports multi-tenancy. In other words, you just need one single Pulsar cluster for the entire organization, like a private cloud, if it's on-prem, or if it is a public cloud, you just need one instance of Pulsar for catering to several teams in one shot, rather than using one cluster per tenant or per team. Which becomes more expensive because each team is duplicating the effort of other teams as well. So now the topics are where the data is ingested in terms of producers produce the data into the topic. And the topic is, you can think about loosely a topic as a stream, and the consumers consume data out of that stream. Now, within a topic, there are partitions because if one topic might not be able to produce and serve data simultaneously if the data rate is pretty high than a single machine can handle. In those cases, we need to partition the stream, and that is where the topic partitions come from. So each topic partition can run it on a different node, so you can spread it across multiple nodes. Then within topics, this is a key difference between Pulsar and the other messaging systems. Each partition is further divided into segments, and these segments are the storage units that are stored in the actual storage system. So this is a key difference between Pulsar and other messaging system that you need to remember, because I will refer to these segments often in the pursuing slides. So now let us look at the architecture of Pulsar. Pulsar was designed natively to be a cloud friendly or cloud native system. So in other words, in cloud, there is a natural separation of the compute versus storage. So the same thing is followed in Apache Pulsar as well. So the brokers are the serving layers and the bookies are the storage layers. So the reason why we split this one is, whenever you wanted to increase the storage, you can increase the bookies. Whenever you wanted to increase the serving capacity, you can naturally increase the brokers, which means both can be scaled independent of each other. So that way, like whenever in other systems where it is a monolithic system where it combines broker and bookies, one of the major issues that you see is when you scale those combined entity, you are scaling both broker and bookie, which means you add storage if you wanted to do serving. So if you want to increase serving, whereas if you add more CPUs, if just you need more storage, right? So that is that's what the Pulsar is trying to differentiate by providing scalability at a different independent layer. So broker is the only point of interaction for clients, and which is essentially producers and consumers. Brokers acquire ownership of topics. Remember, we talked about topics and partitions, right? So at the Pulsar realm, topics and partitions are almost equivalent. So each partition or each topic will be owned by a broker, and it will serve out of that broker. And the brokers, as such, no durable states, essentially stateless. And it also, you can contact any broker, and that broker will redirect you the appropriate broker, which is serving the topic that you are interested in. So the client, the Pulsar client, is smart enough to discover it by connecting to a broker, then reconnect to the appropriate broker where the topics are being served. So if you look at it like in pictorially what I said in the earlier slide, so you have the producers and you have consumers. So some brokers are serving topic 1 partition 1, some brokers are serving topic 2 partition 1, some other brokers are serving some other partitions of those topics, right? So when the producers connects to them, it connect to the appropriate brokers, which is interested in consuming the appropriate topics and its corresponding partitions, and produce data into this. And then similarly, the consumers also connect to the brokers and consume data out of those brokers. Now, consumers have one level of indirection called subscription. The subscription essentially is through the consumers in turn connect to what we call subscription. Subscription is not a physical entity or a connection or whatever it is, but it is more of a logical state that consumers, the broker handles or stores on behalf of the consumer. In other words, the consumers, so subscriptions store the consumer offsets or the consumer offsets where it left off when it died, so that when the consumer comes back again, it knows where the consumer was when it left off, and it starts serving data from that. So in other words, the state management on behalf of the consumer is done by Pulsar itself, so that the consumers that you write are very simple and clean, and not much complexity is involved. But there are different type of subscriptions as well in terms of fault tolerance aspect of the consumptions and other things that we can provide, that which I will talk later. So now let's look at how Pulsar achieves data consistency. So if you look at the data path, the data is produced by the producer, it goes into broker, then the broker in turn replicates the data into the storage layer, which is the bookies. Then the bookies acknowledge that the data has been stored, and then the broker in turn sends the data acknowledgement back to the producer. By that time, data is the acknowledgement is given to the producer, the data is replicated across 3 bookies. So now you can do some quorum consistency or full consistency by configuring those parameters where how many bookies I have to acknowledge before I send an acknowledgement to a producer. You can do 3 out of 3 or 2 out of 3. So 2 out of 3 means quorum consistency, or 3 out of 3 means it's more a full consistency. So then Apache Pulsar also supports durability, where there's no data loss. So what happens when the data is stored in the bookie, it is returned into a journal. That journal is flushed into the disk, like similar to ACID transactions are, not only on one bookie, across all the bookies where the data is being stored. So by the time the acknowledgement comes to the broker, all the data is reached the disk as well as replicated. So by the time you send the data from broker, the acknowledgement from the broker to producer, so the data is secure. So it can survive one bookie node failure or the entire cluster failure or even a data center failure, so that when you bring up the system back, the data is in the disks. So now how does the bookie store the data in the journal? So the writes follow a different path. So the writes, as you can see, first hits the write cache where the it's returned into the cache, and it's also returned into a journal, and the journal is flushed into disk before the acknowledgement happens. So that is the write path. Now since the data is coming through the broker and the acknowledgement goes out of the broker also serves have a small cache where once the bookie acknowledges, then the consumers can consume out of the broker cache, so that it's pretty fast and real time. Now, if you've fallen back from real time, you can read data from the ledger or from the bookie, because bookies have the storage, and you can go back to the bookies to read when it's the data is historical, or you want to read that older data, right? So the read path is very different. When the read request comes on bookies, so you need to have a what do you call index, essentially an offset or message ID that you give into Pulsar, and it will locate which bookie has that, and within that segment it will locate where that message is and start reading from that message onwards. And it goes through a read cache, so it starts from doing some prefetching and all the smarts and everything, so that when you request the next block of data, already it's available in the read cache and the data is served out of it right away. So essentially, what this slide means is the paths for write as well as read as well as serving out of the brokers are completely different, so that mixed workloads involving these different type of access can be in the same system. Now, I was mentioning about the segment, how the segments are, partitions are divided into segments, right? The segments, how the segments are replicated and stored is the intention of this slide. As you can see, a stream as going through, the streams are divided into messages. Messages are bundled into segments, and the segments, when the bookies are writing this data, when they get messages, they assemble the segments, and once a segment is filled up to the appropriate size or time base, then it's sealed. And so once the segment is sealed, it's immutable in the sense like you can't change the segment at all. So like as you can see, the segments is whenever you write 3 copies of data simultaneously into bookies, each one is going to the same segment across different 3 machines, right? So which means the segment when the brokers are close this segment, the segment that is being written across multiple bookies will be closed. The new segment will be open. So which means one of the cool thing about this one is when the node dies, which is in the next slide. So when the node dies, now whatever the current segment that has been being written on the particular node is closed. For example, let us say you're in the middle of writing segment 2 on node 1, 2, and 3. Now, when the node 2 dies, so the segment, the broker will come to know about it. The broker will say, okay, let's close segment 2. So which means it will close the segment on 1 as well as 3. Since 2 is not available, so segment 1 and 2 will segment 2 will close on 1 and node 1 and 3, and a new segment will be open. The new segment 3 will be opened in some other nodes. I mean, in this diagram, it happened to be on the same nodes, but it can be opened on any nodes that are very active. So which means within a partition of a topic, the segments can be returned in anywhere, any 3 nodes, as long as any 3 nodes are available. So which means, well, for one segment, 1, 2, and 3, another segment 2, 3, and 4, another segment 3, 4, and 5, or 3, 4, and 1. So this way, as segments keep writing, when one node goes down, they just write shift to the different healthy machines and keep going. So which means the write availability of the system is pretty high. You don't have to depend on that particular node. Instead, you are dependent on only any 3 nodes. So as long as any 3 nodes are available at the bookie levels, the the system can keep on writing into that. So that is the Pulsar resiliency. Now, so like now, whenever the node goes down, the node can go down for maintenance, or the node can go down permanently in the cloud-like environment, right? So which means we have to bring the replica factor back up to that appropriate level. In the case, you have to bring up to the replica factor of 3. So in this case, we have to initiate re-replication, right? So instead of now, the cool thing about Pulsar is it doesn't have to, since all the data is stored in segments and these segments are distributed across different nodes. So those individual segments are copied into different set of nodes. So essentially, what happens is a multi-node, multi-point to multi-point copy. So I can grab segment 1 from node 1, segment 2 from node 3, and segment 2 from node 2. So those kind of, so since several nodes are taking place in the recovery of the re-replication, so the recovery will be much faster and also does not hit one node constantly. So now, if you wanted to add more nodes into the system, just keep adding nodes. So as the system sees new node, slowly the writes will start shifting into the new node. Within a few minutes, the writes will start shifting over as the data is, as new segments are open, right? As new segments are open, bookies 3, 4, and 5 will be used rather than 1, 2, and 3, and 4, right? So it start writing into those new segments. So now, when the segments become older and older, especially when you are operating in a cloud-like environment, do we have to keep expensive AWS instances to keep running the storage alone, because there is some cost of CPU attached to it, right? So no need. With Pulsar, there's no need. Instead, we can use S3 and configure the tiered storage that allows you to copy these segments, the older segments, into the S3. And whenever you access those older segments through the Pulsar API, automatically Pulsar will know that this segment has been moved to tiered storage, automatically pick up that segment and serve it out of it. In other words, you don't even know that the data is served to be up in S3. Instead, the Pulsar API, you just use the Pulsar API, and it's all transparently done for you, independent of whether this data is stored in the bookies or in the low-cost storage like S3. So this gives you an idea about the same thing that I talked about. So the processing, real-time data is served out of the brokers, which is the tailing reads. Catch-up reads are done in the warm storage, and which is stored in the bookies. And the cold storage, which are historical reads, are served from a tiered storage called cold S3. But all of them go through the same API. Now, what is the advantage of segments? We talked about partitions being segments. What is the unique advantage that it brings? So if you look at legacy architectures like Kafka and other systems, so you have only broker. There's no separation between bookies and broker I talked about. So which means, and also each broker handles a set of partitions. And for some partitions, one broker will be primary. For some other partition, other brokers will be primary. If you take the case of a partition, one partition will be primary, the other partitions will be holding the copy of the data. Now, when the primary goes down, then in order to rebalance the load, the data has to be copied from one broker to another broker, which means the entire partition data has to be copied from one to the other. So that means, that same node will be not only getting data for that broker, but also is involved in the re-replication or rebalancing. So that becomes an expensive operation, which reduces the throughput of that broker drastically down. That's where you see, that's why you have to over provision so much. Whereas in the Pulsar, it is not the case. It's a segment-based architecture. When one of the node goes down, the segment automatically shift the writes to other nodes. And even if the write node, one of the storage node goes down, the re-replication is a multi-point recovery. So which means it's not hitting upon a single node. Multiple nodes cooperatively recover it so that the load of the recovery itself is shared across several nodes. Now, deployment. Another advantages that Pulsar brings to the table is deployment in Kubernetes is much easier. In a Kafka-like system, every broker's port has to be exposed because the client does not do broker discovery by itself. Instead, explicitly you have to enumerate the brokers. So because of that, we need to set up invariant IPs in the cluster, and that is the IPs that you have to give it to the producers and consumers, so that when the brokers move around, the load balance addresses are things that don't have to move around, right? So which means if we scale the number of brokers, then you have to give the IP addresses again for those, then you have to manually enter it for the consumers and producers, then you have to restart it. In Pulsar, that is not the case. So there's only one endpoint the Pulsar exposes, and so that will have a way by which it can proxy into those individual brokers, and all the clients and producers have to know is only one endpoint. So now, because of there's only one endpoint, I can increase the brokers from 3 to 5, 5 to 10, depending upon the needs, and I can increase the storage underneath. So producers and transparents are completely oblivious to all these various operational activities that is going through, right? So that way, what happens is there's, even if you increase the number of brokers, the same load balancer will distribute the load across all the brokers, and brokers in turn will distribute the data to the storage nodes. All of them happen under the covers. So which means the developer is completely shielded from the operational aspect of the after Pulsar itself. So what does it mean, partition versus segments? In Kafka, partitions are assigned to brokers permanently. A single partition is stored entirely in a single node. Retention is limited by and the data you can retain in a partition is limited by a single node. In Pulsar, it's infinite, in the sense if one of the bookies is full, the segments will automatically shift. So each partition is essentially unlimited. As long as the storage is available, or you can keep adding more storage, the system can keep on adding data into a single partition. Then failure recovery and capacity expansion in Kafka requires expensive rebalancing, because every time you add a node, you have to move some of the partitions out there, and you have to recopy the data, move out some of those. That all requires expensive copying. Whereas in our Pulsar, when you add a new node, the new writes are automatically shift into it, right? And rebalancing is an overall big impact over the system, affecting regular traffic as well as the operational traffic. So now let us look at what are the messaging models that Pulsar supports. So typically in an enterprise, there's a need for queuing and streaming, streaming and messaging. For example, whenever you are analyzing the logs coming from your machines versus a worker queue that you have to do in where you wanted to take some item, you want to process it, and there is a somebody who's publishing those items, and somebody is dequeuing the item and process it and move on to the next item as a set of workers, right? So those two paradigms are combined in Pulsar. That's why we call this a unified messaging model. Usually such patterns are require two different systems. One for messaging is for Kafka, and another for queuing is RabbitMQ or JMS queue or ActiveMQ, those kind of systems. But Pulsar unifies both those models into a single system so that you don't need these multiple systems. In so one single system, you can mix those traffic, queuing traffic, as well as messaging traffic, all into a single system. And that is provided by the subscription that I talked about, right? So for the streaming model, there are two subscriptions, and queuing model, there's one subscription. So the data is published into the topic. There is an exclusive subscription. When one consumer consuming out of that subscription, if another consumer tries to consume out of it, it gives an error. Then if failover subscription, in the case of failover subscription, you can have one consumer consuming and other consumer standing by. So the moment the consumer one goes down, immediately the subscription will replay the data from where the consumer one left off to the standby consumer. This is needed in the case where some of the consumer can go down and come up or scale up or whatever it might be the case. For the queuing subscription, if you look at in the other two, all the data from a partition or a topic is consumed in order, like M0, M1 to the same consumer. Whereas in the queuing subscription, that data is spread across multiple consumers because it's a queuing where you dequeue, do the work, and move on to the next item. So one of the key things in this case is what we call as individual acknowledgements. In the worker queue kind of environment, each consumer, one consumer might be going fast, one consumer might be going slow, and it's important to acknowledge individually the message and keep track of it. For example, if consumer 3 is fast and going like M0, M3, consumer 2 is still in M1, whereas consumer 3 has gone on to M10 or M11, right? So now when the consumer 2 acknowledges M1, then we can, at that point, we can, consumer 2 can get M12 or whatever it is, right? So think about millions of messages you have to keep track of the acts. On the other hand, so Kafka does not have this notion of individual acts. So in the Pulsar, like the subscription failover and the exclusive subscription, you have the notion of select cumulative acts. So if we acknowledge that the last consumed that message is M10, you are also indicating that I have consumed all the messages up to from M0 to M10. So that is cumulative acknowledgement. So Pulsar both supports both acknowledgements, and the cumulative acknowledgement is only for streaming subscriptions, and selective acknowledgements for queuing subscriptions. So Pulsar has this notion of inbuilt geo-replication. In other words, you can have multiple Pulsar cluster operating on different regions in a data center across the world, and you can have a unified view of the entire topics and namespaces and tenants across these data center clusters, and data can be replicated. So in other words, one producers can be in one data center, and consumer can be consuming out of the data center or consume out of a different data center. All of them combinations are possible. So it's already inbuilt into the Pulsar system. You don't have to do anything special. Like in Kafka and all, you have to do mirror makers, some separate component that you have to bring on board and everything. In Pulsar, just install Pulsar, bring up the system, and ask the configure each data centers, and it's all automatically the data starts flowing. So simple configuration to add and remove regions. You can even selectively place, like this tenant can be in only data center in A and B, but not on data center C. This also allows you to enforce the data retention policies of the regulations that we need to keep track of. For example, health data in Europe should not leave Europe, right? So those kind of constraints you can satisfy as well. So asynchronous replication as well as synchronous replication, both are available in Pulsar. So if you have asynchronous replication, you can have a primary standby cluster. The data is always replicated. Now, the cool thing about asynchronous replication is when the primary fails and cuts over to the standby, when the consumers are reactivated, you can approximately start from where you left off, because Pulsar has this notion of the markers that is being sent out of the Pulsar that knows what consumer was what offset and everything. Those are all replicated, and those replication when the consumer says this is the same consumer that I was consuming at the last data center, it knows where to send the data. So now you can stretch the single cluster across multiple data center to do synchronous replication too. So Pulsar uses the notion of rack awareness. You can think about the rack as one data center, and whenever you replicate the data at the storage level, you can say, I need to have this replica not only in this data center, also on that data center. So it behaves as like a single cluster, but when the consumers and producers cut over, they exactly know where they left off and exactly what they produced. So which means the state, everything is maintained across these one single cluster straddling across multiple data centers. So this is a viable option when the two data centers are close. If the data centers are a little bit distant with each other, then you might incur the producer latency, because there is a geographical synchronous replication is involved. If the data center latency is around 40 to 45, then the overall latency for publishing will be around 50 milliseconds, because published latency is 5 milliseconds. So the replicated subscription, I don't want to go into detail about it in the interest of time. So as I mentioned, Pulsar is a cloud native and multi-tenant. One single cluster will suffice for an entire enterprise, and you can distribute multiple themes within a single cluster. You can we provide authentication plugins, authorization plugins, and you can isolate each tenant to have certain quotas, flow control, then how much rate you can consume each topic at the particular tenant, particular team. It can be done at the software isolation level. And even if some tenants or some teams are critical from a revenue standpoint, you can move those nodes into a dedicated set of hardware, but still as a part of the single cluster, so that traffic is not even influenced by the other tenants, right? Or if you have a bug and everything that is coming through, you can isolate that tenant separately, then pull it back in the cluster. All these things are well thought through in Pulsar. So this is just a quota. So what are the Pulsar clients? How do you interact with Pulsar? The language-wise, we have multiple languages like C++, C, Go, Python, Java, Node.js has been added. And additionally, there is a native Scala, native Rust, and other languages that are available that is community maintained. How does the Pulsar producer looks like? It's as simple as it can get. Just to open up a URL for the brokers or the load balancer endpoint that I talked about, and create a producer, because the topics are named hierarchically, tenant / namespace / topic. Then send a message. You can have a asynchronous version of the producer message as well. Then how do you consume out of it? As simple as it can get. Just to issue the address, create a client, and subscribe to a multiple one topic, and receive on the topic, then acknowledge. So once it acknowledges, it automatically, you can receive the next message. So Pulsar also provides support for schema registry, especially to provide type safety to applications. Pulsar provides a server side. I mean, if it's client side, it's up to application. The schema registry allows you to provide on the server side. So you can upload your schemas for a particular topic, and the cluster will enforce it. And based on the type of enforcement that you want, like backward compatible, forward compatible, or incompatible, all these things can be enforced at the topic level. So Pulsar schemas consist of a name and a payload for whatever the schema is, and the schema type, whether it's a JSON, protobuf, Avro, and you can addition it to user-defined property like a git SHA of the schema file that you was last that was upgraded into production, right? So if you look at how the schema, create a client with a schema on, you create a new producer, then with a JSON schema of whatever that class size is, then whenever you try to publish it, you have to stick to the schema. Otherwise, depending upon what attributes that you have set on the topic, automatically it will be enforcing that one. So if the schema changes and when you publish it, it will upgrade the schema as well if there is a forward evaluation occurs and with the backward compatibility. Okay, so far we talked about what do you call the messaging side of Pulsar, which is the ingestion, and the storage side of Pulsar, where you can retain the data as long as you want by expanding the storage nodes, or retain certain amount of time after which you can expand the data. We saw the low-cost storage and other aspects. Now, what do you do with the data? You need to process it, right? You can write your the processing comes in the form of multiple different aspects. One is consume data as it's processed, and or the second type of compute is lightweight, in the sense like, hey, I want to grab some data, do some simple lightweight and put that back into the Pulsar itself. Then heavyweight compute in the form of DAGs and like what Pulsar and Flink and all the various frameworks do. Then interactive querying of store data streams. So which means the data is stored in the storage, the stream data. Now we want to query the data. How do we query that? So I'm going to skip a few slides in the interest of time, but let me talk about what the lightweight compute. If you look at the abstract view of a compute representation, you have incoming messages, a function is computing them, you're doing output messages. So that's all it is, right? So now it's usually the DAG form, and you have to stitch the DAG together using a lot of code, or if you're used to Spark and Flink kind of frameworks, you have to use scholar-like notation, the functional map, flat map. Now, the messaging and compute are two different systems usually. Like if you are taking Pulsar along with Flink or Pulsar with Spark, then it's two different systems with two different evolution aspects, right? But they do deliver a highly scalable system, but it's a powerful API, but very complicated for users to learn. And most of the time, it creates some kind of operational issues and developer issues. So what we did is, what are the lessons that we learned after the streaming experience, right? Most of the time, people do simple tasks like data transformation, data enrichment, data classification, routing data to from point A to point B and C, and data extraction and loading, and some simple aggregation and writing microservices. So with this in mind, we needed something very simple, like so we got inspired by the Lambda functions in Amazon and Lambda functions in cloud as well as in Azure. So simple functions are submitted to system, runs per events, composition APIs to do complex things. It's really popular. Why can't we borrow all these ideas? So that's what we did is what we call as a stream native compute using functions. So the Pulsar has a notion of Pulsar functions, and it provides the simplest of possible API, support for multiple languages. You can write it on, and you can use a native language function definition itself, not write your task. Then it scales developers. You don't have to learn a new API. Even if there is a small API, just 1 or 2 lines of API that you would learn. And you can use the message bus native concept. Inputs to function is a topic. Output is from a function is the topic. So Pulsar functions, exclamation function, if you are, this is how it looks like. It takes a string, add an exclamation to a string, and outputs a string. So I think I'm running out of time. So can you get a couple of more minutes? Okay. So this is how it looks like. So the string input is added with the exclamation character, gives a string output, and your input to string, the input is the input topic that is specified when the function is submitted, and output of the function is an output topic that is specified when the function is submitted. Now, if you wanted to get a little bit more sophisticated, you can, instead of using a Java function, you can use Pulsar function and you can type it. So type the input as well as type the output, and you get an extra, this thing called context. The context allows you to do some state manipulations and everything aspect of it. So functions are executed for every message of input topic and supports for multiple input. As the functions support multiple arguments, we have multiple topics as input. And functions also supports void functions, so which means there is no output from that function. And you can integrate with Schema registry, and custom Saturday and serialization delays can be provided by the users. So it provides all the three semantics of the usual, at least once, at most once, and effectively once. And the Pulsar functions can be dropped as a thread in the broker, or it can be dropped in a different, as a process in the different nodes, or it can be dropped into the pods as a Kubernetes in the Kubernetes cluster, so that can work alongside broker, or but even though it's isolated traffic. So functions can store state, especially in the case of aggregations, when aggregations that happen across multiple functions. So there is a notion of the context, and the context and increment counter for word count. Essentially a state manipulation that is going on. The state is all global at this point. So every time the update is global, so when the one of the function fails and restarts somewhere else, it can pretty much don't have to recover the state because the state is already there. So you can you can have the notion of Pulsar IO, which is essentially the what do you call getting data in and output to the function Pulsar system. So I don't want to go through this one because okay. So Pulsar has a lot of growing ecosystem. Then I think this is not updated for 6 months now. It has grown exponentially. A lot of companies are using Pulsar. Pulsar already in production on several companies. As far as I know, there are 600 plus companies already in running in production. So with the lack of time, I'm done. If you wanted to have a slide deck, I will be happy to share with you. If you wanted to read more about Pulsar, there is a couple of blogs written by an author called Jack Von Lightly. He has done a lot of experiment with Pulsar, and he also understood Pulsar also. And there is more topics as well. These are all, it used to be part of a Streamlio. Now it's all available as Pulsar blogs, as a Splunk blogs. So you can read it in the Splunk. If you search for this Splunk blogs, it will automatically show up on Google. So that's all I had. And thanks for listening. If you want to reach out, I can reach out on the Slack. I'll be there for half an hour. So organizers, can you please forward the logistics for the Slack so that I can happy to answer some other questions. Thank you. It was a pleasure talking to the audience.